One kind of alloy is in the left side of the system, which is steel, where the weight percentage of carbon is up to 2% basically. And if the carbon amount is more than 2 weight percent in the iron, it becomes cast iron. And mostly we use steel rather than cast iron. Why? Because cast iron are brittle. Steel are somewhat ductile. So we use, or steel have more tensile strength compared to that of cast iron, you can say. But there is some advantage of cast iron, that is cast iron have high compressive strength. So when the application required high compressive strength you understood? Suppose this is the pen, I am compressing from both sides. I am pushing it from both sides. If it will crush, it has low strength. But if it will not crush, it has good strength. So cast iron also is same. If we apply load from both ends and it is compressive in nature, compressive means you understood? This is the example, you are applying load in this direction, both. So that cast iron is good in this case. It can withstand the load. But if you apply tensile load, for example, like this to cast iron, it will break. But if you apply tensile load to steel, it will good. It can withstand the load because it is somewhat plastic, right? It will undergo plastic deformation. It can be protected. But cast iron, lot of cementites will be there. Maybe your graphite will be there. So the crack will start from the graphite or maybe from the cementite, and it will flow easily. Crack initiation is easy. Okay, fine. I don't have much time, otherwise I can discuss lot of things. I have admission duty. Anyways, so can you tell me why cast iron will not undergo failure when you are applying this kind of load? Just tell me. The load is compressive, but cast iron will not fail easily. But it will fail in case of tensile. Why? It's tough हो गया, but tell me technically. You have studied the graphic theory? Graphic theory you have studied, no? The crack, what? In DVM, deformation behavior, you have any flaw, like as a fracture mechanics, you have studied somewhere. Anyways, fine. If you check any material, you cannot say that there is no defects. Any material you take, some defects will be there. Suppose you imagine you have cast iron and there is a flaw. Flaw means a small crack is already present, for example. Or if atoms are not so close, that can be considered as a crack also, because that is the empty region, right? This is, for example, the situation. A small crack is there. Here also a small crack is there. That is the flaw. So how the failure occurs? If the crack will propagate and it will become two part, right? Similarly, if it will propagate, it will become two part. That is the failure, right? But why cast iron is good in this and why cast iron is not good? The C you can understood. See the direction. Because of compressive load, the crack will not propagate. It will close up. Otherwise, it get closed. Closure of the crack will occur. But if you apply tensile load, right side, so it will become more wider, and it will finally propagate and failure will occur. That is the advantage of having compressive load sometimes. It doesn't mean that steel don't have good compressive strength. Steel also have good compressive strength. But I am comparing these two, cast iron and steel. Anyway, it is I think you understood, no? Okay, very good. And if you see, you know that iron, we don't say iron carbon phase diagram basically. If you go through the books also, they are writing it is iron cementite metastable phase diagram. If you see books, that is not actually iron carbon phase diagram. It is iron cementite. Fe, Fe3C, and a word is called metastable. It simply means the iron will be there and cementite will be there, but no carbon will be there in the system as a free form. That is the meaning. If carbon will be there in the free form with iron, then you can call iron carbon phase diagram. And carbon free form means graphite. Graphite is the purest form of carbon. We know that, 100% carbon. Right? And why the word is metastable? Iron cementite metastable. Because cementite is metastable in nature. You have studied the thermodynamics, right? You have also studied the phase transformation, right? We can have stable phase, metastable phase, and unstable phase, right? So cementite is a phase which is metastable, neither so stable nor so unstable. So it means if your system is iron cementite and you put it in normal atmosphere for long interval of time, nothing may happen. But if you put it for like more than 1,000 years or for million years, maybe the cementite will decompose into iron and carbon finally. That means Fe3C will break down and it will become iron and carbon. Iron is already there as iron, but cementite part will decompose into iron, Fe and C. But if you take the iron and cementite system to elevated temperature, maybe 660 degree, 650 degree, then suddenly phase transformation will start. Iron will remain as iron, but Fe3C will break down into Fe and C. So that's why cementite is metastable. It cannot stay for more interval of time. Okay, I think you understood my point. So what is graphitization? So graphitization simply means formation of stable graphite phase. Simple, there is no strong definition. Formation of stable graphite phase is called graphitization. And what is the reaction? And as I told, we have what? Iron and Fe3C. This is our system basically. And I told this is metastable. So what will happen? If Fe3C will decompose into Fe, 3Fe plus C, so this is graphite. This is pure carbon. And this is iron. You understood my point? So this basically occurs during cooling, you can say, and also during heating. Also sometimes if you heat also. In what case heating? If it is in room temperature, if you are heating to elevated temperature, it will decompose. Similarly, you start with molten iron. When everything pig iron is in molten state, for example, then you are slowly cooling. If cooling rate is very slow and driving force is very high, it may form cement. Instead of cementite, it may form your graphite. Is it okay? So in other words, I can say the carbon can remain in two forms, either in form of graphite or in form of cementite. So alloying element which makes, this is important. Sometimes in the GATE exam they ask this question. They will give options and ask you which from these elements which form graphite. I mean, if that alloying element will be present in the iron carbon system, it will help in the formation of graphite rather than cementite will form. Okay, so that element is basically silicon. If lot of silicon will be available in your iron carbon system, instead of cementite, graphite will form, maximum chance. So that means silicon is the alloying element which help in the nucleation of the which phase? Graphite phase. Because you know the solidification starts with nucleation and growth. First nucleation will occur, then growth will occur. Some solid state phase transformation occurs by nucleation and growth also. A phase will nucleate to small phase will form, then it will become bigger. Okay. Nucleation and growth. Okay, fine. And other alloying elements are aluminium and nickel. You can write, these are the three examples. Silicon, aluminium and nickel. We did it actually. Recently we did that. In my research, I am doing research on red mud, I told you once maybe. While teaching mineral processing, we are extracting values from bauxite residue, red mud. So we produce iron from that. But the interesting point is that iron is not iron. We got cast iron directly. So a lot of research has been done on that. They produce iron, but we produce cast iron. Why? Then I checked the elements what are present. I found aluminum was there. I found silicon was there. So that's why the result is cast iron. We got iron, matrix and flakes of graphite. That is very interesting. We proved it actually. It is already proved concept, but we got it and we can correlate with the previous researchers. We did it actually. So if silicon will be there, aluminium will be there and nickel will be there, most of the chance you will having iron and graphite. And you understood up to this? And how? Okay. How means how? That means you might have a question, how silicon helps in the formation of graphite rather than your cementite, of course. I will not go into the depth of the thermodynamics right now. You have heard about interaction parameters and all? Okay, very good. Excellent. Interaction parameters you know. So there are certain alloying elements which have positive interaction parameter and some alloying element have negative interaction parameters. Because if that alloying element will be there in the system, they will interact with other alloying element. So carbon is the other alloying element. So when you add silicon, so silicon will start interacting with carbon in a positive way. So it is the positive interaction parameters. That is one of the point. So carbon have a positive interaction parameter with the silicon have a positive interaction parameter with the carbon. That is one point. So it means what? What will happen to the activity finally? If positive interaction parameter will be there? We have studied this, no? Activity will increase or decrease sometimes. Or activity coefficient will increase or decrease. Basically what happens, if silicon will be there, then activity coefficient of the carbon will increase. And you also understood, if activity coefficient increases, that means activity will increase because activity is equal to activity coefficient into mole fraction. We know that. You have studied in thermodynamics, right? Solution thermodynamics. Don't deny it right now. No, activity is equal to activity coefficient into mole fraction. We know that. Right? More is the mole fraction, more is the activity. More is the activity coefficient, more is the activity. So activity increase means what? If I will increase the activity of you right now, so you can easily move out of this class right now. Maybe. Again your activity will decrease, you come back again into the class, maybe, right? So whenever activity is increasing, they can come out from that or they can move from that. So just imagine you have cementite, Fe3C, and you increase the activity of carbon. What will happen? It will come out. Its activity has increased now, it will come out, it will not stay. But if you decrease the activity, it will become stable and it will stay in the cementite. You understand my point? So you have liquid molten pig iron, for example. It has iron and carbon in molten state. There is no graphite, there is no cementite initially. All are free atoms. The moment you do solidification, either iron will form, of course, but carbon will either remain in cementite or in graphite, free form. So if silicon will be there, what will happen? Silicon always increases the activity of your carbon. So carbon will not stay in any phase, not in combined phase actually, because cementite is a combined phase. Your solid solution is also considered to be combined, but not exactly. Like austenite is there. Austenite carbon is there inside the interstitial sites. Ferrite, carbon is also there in the interstitial sites. It is trapped, you can say, trapped. So my point of view is, you can have only free iron and free carbon if lot of silicon will be there. They will come out. They will come out from the ferrite, they will come out from the austenite, they will come out from the cementite. So all the carbons are free now. So this is because of increasing in the activity coefficient of the carbon. Okay. So there are certain alloying elements which can increase the activities, which can decrease the activity. I will not go into the iron making, although I can give a lot of examples related to iron making also. Anyways, where activity goes. Stability phase graphite form. Okay. Stable phase graphite form. Okay, so you understood. So stable phase graphite can form from what? Liquid solution to carbon. This is one. The next, can you tell me? I told you already. Oh, next please. Next, it can form from anything else? Yes. See, in the left side, if you see carbon is trapped, either as a solid solution or as a compound. Fe3C is a compound or in intermetallic sequence. But others are solid solutions, and liquid is also solid. So liquid means liquid molten iron I am talking about. And these are all graphites. And which is helping silicon. If silicon will be there, it will form this kind of thing. And another interesting point is, can you justify that liquid molten iron will become carbon plus Fe? And you know that you have studied about driving force also, I think, or you forget. In physical metallurgy, there is a concept called driving force. That means higher is the driving force, nucleation will be easy. Because for example, you have liquid iron, you want to make solid iron, how it will occur? It will occur by first nucleation stage, then growth will happen. How nucleation will happen? Nucleation will happen if driving force available is more. If driving force available will be less, nucleation will not occur. Sometimes nuclei also form and dissolve again. You also know that. That is the size of the nuclei. Critical radius. Yeah, you know this. Very good. See, these are very important because in the interview they will ask simple questions. Nucleation, what is nucleation, what is growth? Okay, I am not going into details right now. Quickly I will draw the iron carbon diagram to see. See, which one is the, this is very important point, you know. Oh, sorry. This one, this see, what is this point? Eutectic point, not eutectoid, eutectic. Why that is called eutectic? Liquid is, I mean, what is the significance of eutectic point? If you have a eutectic point, what is that significance? But what is the advantage you can get out of that? You are working in a melting casting plant, for example. Your boss asked today, you are a BTech in metallurgy, I am from mechanical. Just tell me what is the advantage of having eutectic alloy or eutectic point? Or can you make some eutectic point? You will ask. What is the advantage? Yes. If you have a eutectic point in your alloy system, that means you can have minimum melting point. If you start heating the solid from the liquid, at that point it will become molten. That is the lowest melting point, no? Right? Because just see, pure iron is how much? For pure iron you need to go from room temperature to this much temperature, see, very high. But if you have a eutectic alloy composition, iron carbon, just go to this temperature and you get molten iron. That is the advantage, no? The minimum melting point is called eutectic point. And that is very advantageous because you can easily cast it. The flowability will be good, the castability will be good. That's why people call cast iron is very good. Why? Because its flowability is very good and its castability is also very good. You can easily cast it, melt it and pour it into the mold very easily because it is very lower melting point. Cast iron has high carbon. So you might get a question in the exam like this, or in interview they ask this one. Why iron carbon system have low melting point? So you can draw this diagram and show them. See, this is the pure iron melting point, but the moment I am adding carbon, I am increasing the carbon. This line is going down, and this line is called what? Liquidous line, if you remember. No, this is the liquidous line. This line is liquidous. Liquidous line means what? What exactly? It is a boundary. Liquidous line is that boundary above which everything is liquid. In simple way, you can say. But below which you may have two phase, solid, liquid, or maybe solid. It depends. Similarly, solidus line is that line below which everything is solid. But above which you may have two phase or you may have liquid. It depends. See, this question sometimes during my placement they ask me, during my BTech placement. They ask me why this cast iron has low melting point but pure iron is not having. So I draw this diagram and I explain them. They were very happy in that. Just by looking at iron carbon system, you can explain them. If you increase the carbon, melting point go down actually. So that is again advantage during production of pig iron by using blast furnace. That is why we are tapping the iron at only 1400 degrees centigrade. But it is not possible now because pure iron melting point is 1538, 1539 sometimes. But you are tapping it at only 1400 degrees because lot of carbon is there in pig iron. That is the reason. Okay? Do you understand my point now? Okay, very good. Then, yeah, what I am talking about, this is very interesting. See, so room temperature is this one, and your melting point is this one. But right now it is not melting point, it is liquidous temperature. Why? Because this is an alloy. Melting point is pure metal melting point. You should not confuse. Difference between alloy and pure metal is that. Pure metal means it has a sharp melting point. It will melt at a particular temperature. Similarly, eutectic alloy also have a fixed melting point. But if you change the composition, it is variable. That is interesting. Somebody may ask, what is the similarity between a pure metal and a eutectic alloy? What you can say? Both have sharp melting point, same melting point, they will melt or solidify. But if you change the composition beyond that or less than that, you have a range of melting point. Okay, you understood my point? So alloy systems basically have range of melting point. They will not suddenly melt to liquid. They will slowly melt to liquid. Because some alloying element have high melting point, some alloying element have low melting point, and you are making an alloy. So pure metal have only sharp melting point or eutectic alloy. So this is a eutectic alloy, you can say. Fine. So now my point is just see the difference. This difference is called what? If you remember, delta T. Delta T. But actually consider this one and where solid is forming. Yeah, sorry. This I am not talking about this one right now. Consider there is some confusion. Just consider this, not this one. Consider this one and this one, for example. Let it be this one and this one. This temperature. This is delta T. Why? Because below this solid is there. That's why. Below this solid is there. But this is the room temperature. But below this solid is there. This is liquid phase. No? So this difference is actually called undercooling, if you remember. Delta T. Suppose your molten iron is at around 1600 degrees centigrade, and you can see you have this kind of alloy composition. This kind of alloy composition, molten iron is suppose 1600 degrees centigrade, let it be, maybe. And solidification starts from here because liquid will convert into gamma plus Fe3C, if you remember. But here Fe3C will not form, carbon will form. Instead of Fe3C, gamma plus carbon will form. Okay. So if you increase this one, what will happen? More driving force will be available and solidification will be easier. Very good. Suppose you start with this temperature, you suddenly bring the temperature to this, for example. So what will happen? Then again you are increasing the driving force. Of course, if you hold it here, then this is driving force. But if I will move it to this, I will bring it to that temperature quickly. So more driving force will be available. So what happens exactly? That eutectic point is raised by some temperature. That particular eutectic temperature. What is the eutectic temperature in the iron carbon system? 11, 47 or 45, 46 different books. Fine. But if you add silicon will rise the eutectic temperature somewhat. It becomes 11, 54 or 53. So because of this, you have more driving force available. Okay. Because of addition of silicon, the eutectic temperature will rise somewhat. That is 11, 54, 53. Fine. So because of this available driving force, you are now suppose cooling very slowly. So sufficient time will be available. All the carbon will diffuse out to form pure carbon and you have iron. So what is the difference between iron carbon diagram and iron cementite phase diagram? Iron carbon diagram will be having iron and carbon only. So wherever there is cementite, you replace all the cementite by using carbon. Like gamma plus cementite, you make gamma plus carbon. But condition is you should cool very slowly and you should have alloying elements like aluminium, you have silicon or nickel. But major alloying element is silicon. Silicon is very important. Okay, fine. So primary, I'll take 1-2 minutes more. Secondary, okay, we have two types of graphitization, primary and secondary. Primary means this one, this is the primary. When directly liquid molten iron will convert into iron and carbon directly from molten state. But suppose iron and cementites form in the system, so in solid state now, and that cementite is decomposing into your iron and carbon. If you have already formed a solid system where austenite is there, you have ferrite is there, and they are also decomposing into iron and carbon, free carbon, then that is also called secondary graphitization. Primary graphitization means from liquid, directly from liquid iron to solid iron and carbon, solid carbon. Understood my point? The first one. But all others, alpha into carbon plus Fe, all the second things, okay, these three are actually secondary and this is primary. Very simple, no need to remember. Okay, this is coarse graphite to fine graphite. See, basically what happened in the real situation, if you see the graphite flakes, okay, do you remember the cast iron structure, how it looks? Take it out. It will be like this kind of flakes will be there. So these are graphite flakes. Graphite flakes will be there. But graphite flakes are very coarse, and you know that coarse structure are not good always. We always need fine, small size. And if it is spherical, then again advantage, right? So the problem with these graphite flakes when it forms are bigger, coarser in nature. So the question is what? How we can convert it into fine? So there is a concept called inoculation. You can write, huh? There is a concept called inoculation. And that alloying element is called inoculant. Inoculant. That is basically one example is ferrosilicon. You can write one is ferrosilicon and one is calcium silicon. Ferrosilicon and calcium silicon. One is ferro and one is calcium silicon. Ferrosilicon means what? FeSi. Calcium silicon means CaSi. So both are having molten iron, but you are adding FeSi or calcium silicon into this. But in this molten iron, you are not adding any kind of this kind of things. So what is the changes? You will end up with, when it will become solidified, you will end up with coarse graphite flake. But if you see this structure, you will end up with very fine graphite flakes, which is essential actually. Finer structure are always better. They will provide good strength always. Inoculant means you might have a question. Why, if you add, then property you also change. Of course, your alloying elements are there. So the point is they are added in a very small amount, negligible amount. They will just help in the nucleation stage. Nucleation of graphite will form, and that nuclei is very small nuclei actually. They will not grow with time. So inoculants are those alloying elements which are added in a very small amount, and their function is only to form very fine size of graphite flake. That means, you know that how liquid will become solid? What is the main condition why liquid will become solid? One condition is you have to bring the liquid from high temperature to below the transformation temperature, solid transformation temperature. Forget about that. But liquid always forms on solid will form when there will be solid available already. If there is not solid available, liquid will never form. So that is the why liquid will become solid at the boundary. You have studied nucleation and growth. Boundary wall acts as a nucleation site. Because boundary wall is already solid. You have a liquid molten pool. But in the middle it will never form. It will form at the boundary wall. Because that is called heterogeneous nucleation. So similarly, if you add a solid and mix it, and that solid will remain as solid, it will not become dissolved. So then what will happen? That will act as a nucleation site. So inoculant is like that only. That means inoculant melting point is very high compared to the molten iron. You understand my point? To make a liquid to solid, you need a solid. You have initial solid, then it can be formed. So inoculants are those alloying elements whose melting point is high. If you add them in a small amount, they will go, but they will not dissolve. They will remain as solid. So around that solid, this solidification will start. The graphite flake will form. Graphite is a solid, initially a molten liquid, so that flake is very small. But that is one point. And the point is see how to produce graphite nodules. Just see the graphite flake. Graphite flake, the edge of the graphite flake is sharp. Just see, pointed. Graphite flakes are very pointed at the edges. Those will act as a stress concentration site. If you apply load on the material, on the cast iron having graphite flake, the concentration of stress will be maximum around the edges, at the sharp edges. So crack will initiate and it will fail. So what can be done? You convert it into nodules, spherical graphite. That can be done by heat treatment. We'll discuss that in coming lecture. But one thing you can do, what? You can add, if you want to do during solidification, very interesting, just add cerium and magnesium in a very small amount. Cerium and magnesium. So cerium and magnesium will do what? It convert the graphite flake into nodular form, spherical. That is called SG cast iron, spheroidized graphite cast iron. Okay, we'll not discuss much today. I'm leaving now. Spheroidized graphite cast. That means the graphite are not in flake form; they are in nodular form. That's why the name is spheroidized graphite cast iron. This is very interesting. But suppose your question will be: suppose we are not adding any kind of cerium and magnesium during solidification, but that means we will end up with graphite flake, but still we want nodular graphite. So heat treatment will help you. There is certain kind of heat treatment. If you do, it will become nodules again. That is very interesting. That is the significance of heat treatment only. We are discussing heat treatment. That's all. Okay, from the next class maybe we'll discuss something interesting about effect of alloying element. So I suggest you please go through this part. If you add a particular alloying element, what is the effect on the steel property? At least. If you add aluminum, what will happen? If you add silicon, what will happen? If you add manganese, what will happen? If you add vanadium, what will happen? If you add tungsten, what will happen? If you add titanium, what will happen? If you add any carbon, what will happen? So please go through that. That is a very important one.